Testing. Testing? Yeah. Testing? Yeah, I think that's okay.
Oh, nice. You have separate channels for each of them.
Yeah.
Is it directional or is it? Yep. Yep. Hello, hello, hello. Can you hear me?
It's fine.
All right, perfect. This looks great, I think. Does the audio get piped out from speakers at the back? Or
What's that?
does the audio get piped out from speakers at the back, or is it built in here somehow?
I think so. Those girls.
Oh, those aren't HVAC. Interesting. Perfect. Okay, this is great.
There you go. Good. Good. Down good in live stream.
Is the live stream link in the
Have you done this big of a venue or? Oh, is it like I thought it was gonna be? I thought it was those are in bars, right? Or
So it got so big. They
whoa. What do you turn on that green? It's hot, Mike. Oh yeah. Oh nice. Oh yeah. Yeah, I think so. Yeah, the weather is good. I mean, this is the first time we're gonna do it at the observatory and the rooftop. Yeah, I think we're gonna do both for accessibility issues. But yeah, it looks good. So we're gonna observe, and uh, it's a limited choice in New York, but I'm not sure. We have a new telescope where it's very like user friendly. Like it guides and it stacks too, so you can observe like the ring nebula actually. Yeah, you can observe the ring nebula if you do like 15-second exposures and like 30 stack. Yeah, something like yeah. So yeah, it could do that. It's a recent investment.
I saw it. I heard it, but not in action. There was like a fence of Columbia.
and get started. Thank you all so much for being here with us. We're really excited to have you. We're always excited, but we're more excited than usual today because the construction on the roof is finally done, which means we can finally invite you all to the historic dome on top of Pupin if you're interested for some observing after the show. So thank you all for your patience as we got a lot of, I don't know, for the timeline for months now. All right. But before then, we have a really, really interesting talk that is a cool intersection tonight that I'm excited to see. We'll start, as always, with some announcements and with trivia. So we'll have trivia, announcements. We'll hear from Dr. Karthik Iyer today. Then we'll have Q&A and a raffle. And then we are stargazing. Woo! Yeah, good weather. It did not look promising this morning, but the cloud said 8 p.m. You want it to be clear? We'll make it happen. So, all right, how trivia works is there 5 questions. These are supposed to be fun to check in on your prior knowledge. I'll show a question. You'll have time to think about it and chat with others. Collaboration is strongly encouraged in science. And then I will ask you to vote. I'll say 3, 2, 1, vote. You'll show me 1 for A, 2 for B, 3 for C, 4 for D, 5 for E. And we'll see what the consensus in the room is. All right, question 1. How many years does it take for the sun to go 1 round around the galaxy? So I'll give you some time to think about it. We've got some confident folks already. All right, 3, 2, 1, vote. Let's see your answers. Okay, I see a lot of 2s, some 5s, some 4s, some 1s. And the correct answer is 225 million years. So it takes the sun 225 million years to do 1 lap around our galaxy. The sun is moving very, very fast. It doesn't take that long because the sun is moving slowly. So that should give you an idea of how big galaxies are. All right, question number 2. What type of light does the James Webb Space Telescope detect? So these are all different kinds of lights across the electromagnetic spectrum. Our talk today will be about James Webb. So what kind of light does it collect? I'll give you some time to think. Okay, let's vote. 3, 2, 1. What are your answers? I see some 2s, some 5s, some 1s. Maybe no 3s. Maybe a 3. Okay. And the answer is infrared light. This is the best kind of light to observe galaxies that are very far away. So the goal of James Webb is to look at things, especially galaxies that are very far away. Infrared light is red lights. If you have ever watched a spy movie or an action movie and they put on goggles that let them see at night, that's looking at infrared light. So our eyes don't naturally see it, but we can build machines that can detect it, like the James Webb Space Telescope. Question 3. Who among these has a telescope named after them? Okay, 3, 2, 1, vote. All right, I'm seeing a lot of fives, some very confident fives, a 3, or I see a 1 and a 5. We do love to trick you all, and this is a trick because there are 2. So this image is of the Hubble Space Telescope. It doesn't usually have George Lucas's face on it, but that was a red herring for you all. But Vera Rubin was an astronomer who made the first detections of dark matter in galaxies, and one of the largest, newest observatories U.S. quarters that have Vera Rubin's face and information on them. All right, question 4. NGC 2936, the boring name of this galaxy, is an object in the constellation Hydra, is more commonly named for its resemblance to what animal? And this is an image of it on the slide. Okay, 3, 2, 1, vote. I'm seeing some 1s, some 5s, some 2s, some 4s. All right, this is another 2-answer one. Penguin or porpoise? See a penguin or do you see a porpoise? So hands for penguin. Okay, and hands for porpoise. All right, I feel like that one wins consensus. The penguin is, imagine this is the penguin's egg and the beak is here and it's looking down at its egg. Astronomers are not very creative when it comes to naming things. It's either unit question, so this is our weird unit question. A deep field that stared at what seemed to humans like an empty spot of space for a long time, and it detected all of these galaxies. So how many are there in terms of number of astronomy papers? All right, let's vote. 3, 2, 1. All right, I see some 2s, some 1s, some 3s. So there are thousands of galaxies in this image that are visible. So the number of total papers in 2025 so far is 70,000 papers. These are ones that have been posted. So all of the papers that have James Webb in their title is about 5,000. So that one's closest to the number of galaxies. But the longer we stare at this, the more galaxies that would be detected. All right, round of applause for everyone. And I'm excited for all of us to continue to add to our knowledge tonight. As always, make sure you're on our mailing list if you're interested in our events. It's the best way to know when they're happening. We have one last talk for this fall semester, and that will be December 12th, and we'll hear from graduate student Jennifer Mead on telescopes. And without further ado, I'll hand
Can folks hear me? Excellent. All right. It is my utmost pleasure to be here. I am so very happy to, talk to you all this evening and tell you about some of the work that I've been doing with a bunch of collaborators. This topic is very close to my heart, and it's actually a talk split in two parts. So one half is going to be about AI and machine learning and how we use that in astronomy research. Another half is going to be about all the stuff that we're doing with the James Webb Space Telescope and, all the science that we're producing as a result of it. So the talk's going to start. I'm going to talk to you about JWST and why we care about distant galaxies, and then talk about all the papers that you saw from the last question and how we can, use modern tools to keep track of all of them. So let's jump straight into it. All right. So I work with observations from the James Webb Space Telescope. I look specifically at images like the JWST deep field and try to figure out how galaxies are forming. And the reason I can do this and the reason, astronomy is exciting to a lot of people is because telescopes are essentially time machines. So the way this works is that objects that are far away from us, emitting light, spend like the photons that get emitted from distant galaxies spend many billions of years traveling at light speed to reach our telescope. And so when we finally do collect those photons and process them and make them into an image that we can see, we observe these galaxies as they were in their infancy. So we see them when they were very young. And this means that when we look at galaxies that are different distances away from us, we see them as they were at different times in the universe's life. Populations of galaxies evolve at different epochs in the universe. And the way we then do science with them is to come up with physical diagrams like this, where this diagram has three axes. So there's a time axis that says the universe was this old at this point, right? So 0 would be the Big Bang, and 13.7 billion years would be now. There's a log stellar mass axis, which is basically how many stars does a galaxy have, very roughly. And there's a star formation rate axis, which is basically, is this galaxy forming a lot of stars, or is it not forming many stars at all, and it's just sort of chilling? And we use telescopes like JWST to then look at the same galaxy across many different wavelengths to get something that we call a spectral energy distribution or a spectrum. This is basically looking at the same galaxy in the ultraviolet, in the optical, in the infrared, and so on, sometimes using different telescopes. And we then use that to estimate things like how massive these galaxies are and the rate at which they're forming new stars. So this allows us to get a physical understanding of where this galaxy is in terms of its life cycle and star formation activity. We then do this for many different galaxies. So this is actually using observations from the Hubble Space Telescope to then look at how entire populations of galaxies look like at different redshifts or at different times in the universe's history. And then we connect them to try to figure out what their average evolution is. The stuff that I like to do is try to pick individual galaxies and figure out something called the star formation history. So this is a trajectory that an individual galaxy would take in its lifetime as it travels through these different epochs. So the JWST is one of our most ambitious figure out how to exactly make this work once it goes out in space and unfolds like an origami flower. And using JWST, we have been able to see a whole bunch of different galaxies of many different types in such exquisite detail that in addition to doing the star formation history, we also just spend a lot of time studying each galaxy, figuring out why it looks the way it looks and what its properties are and how stars form and so on. So going back to this thing about JWST being a time machine, essentially with Hubble's instrumental sensitivity, right? Like how good, how sensitive it was to very faint light, and its wavelength range, it was able to go a certain distance and really find out that like there's galaxies that are forming at redshifts of 10, of redshifts of 8, when the universe was just like 500 to 700 million years old, which is about 5% of its current age. But JWST can go even farther than that, partly because it's observing in infrared light, which means that it can detect objects that are redder and therefore sometimes farther away because of redshift. And it can push basically our ability to observe things almost all the way back to the cosmic dark ages when the first galaxies and the first stars formed. So observations, with this telescope have been revolutionary. This is just one of the first surveys that I got data from that I was working with called SEERS. And I was just sitting with my iPad and just going through individual objects and annotating them, being like, what the hell is that? And it's so much fun to do this. I still sometimes go back to an observation and just try to find interesting objects to look up. And just to show you an idea of what the improvement has been like, this is the same JWST deep field observed with the Hubble telescope, right? It's a great image. You can see that central cluster right here. That's a massive galaxy cluster, and there's a bunch of objects around it, and so on. This is James Webb, right? Let's just to contrast this a bit. Like, there's two things that immediately pop out. One is that there's just so much more detail. Like, if you look at galaxies here, like you just see that for individual objects, you're just seeing them in a lot more detail. And you can study like the low surface parts of these galaxies. And the second is sometimes you see objects that just weren't visible with the Hubble light, just because it didn't go far enough into the infrared. Right? So there's objects in parts like this that you now see with JWST. That, again, like this allows us to push forward in terms of the redshift frontier by a significant amount. So, JWST has produced a lot of images that have made for really good NY Times articles or, computer wallpapers and so on. But in addition to all the cool stuff, into studying what happened in the first billion years of the universe. And this comes down to these three big questions. When did the first galaxies form? What were the properties of the first stars when they formed in these galaxies? And how do the supermassive black holes that we see in the centers of galaxies today, how did they form? How did they assemble? How did they grow to become so big? So this is all stuff that it's trying to do. And I'm just briefly going to say what's the state of the field in each of these. So in terms of when the first galaxy is formed, what we do is we observe in blank patches of the sky like this, we observe distant galaxies and we get their spectra to try to figure out how far away they are by looking at how much these spectra are shifted towards the red end, often called redshift. And so here you see that there's things going from redshift 10 to redshift 13-ish. Then more recently, we found something at redshift 14.3. This is at 14.4. I think this is the current record holder in terms of a confirmed distant galaxy. This is barely when the universe was about 300 million years old. And then we have candidates for things that go almost all the way up to 25 that we need to confirm. So this is really interesting because back when Hubble launched, people thought the farthest redshift something could be was something like 1.5 or something. And then the Hubble Deep Field came online and saw galaxies at redshift 6 and redshift 10. And now this is pushing that so much farther. It's just showing us that galaxies have been around for much longer than we thought they were. In terms of supermassive black holes, there's this emerging class of objects that have been discovered with JWST that people like to call little red dots. And as Amanda said, we are not very imaginative in how we name things. And these little red dots seem to host really massive black holes very early on. And that puts very strong constraints on the mechanisms by which they can form. And finally, this is the part that I tend to work on the most. So we are trying to now figure out how the environments in terms of the gas and the sort of galactic nurseries that the first stars formed in are observable directly with JWST. So what we do here is not directly look at entire galaxies, but we try to look at patches of sort of resolved patches within galaxies to try to figure out what the conditions are in which stars form. And I'm going to show two quick examples. So one was this thing that we saw again in the Webb deep field called the Sparkler galaxy. So the Sparkler galaxy looks like a 4th of July sparkler, and it has all of these tiny dots surrounding it. This was not something that we were able to see with Hubble. And the reason this galaxy is interesting is because of an effect called gravitational lensing, which essentially happens when there is a massive foreground galaxy or galaxy cluster that bends and warps the light of things behind it that are a lot more distant. So the sparkler is something like this, sitting behind a massive galaxy cluster. Imagine like there's a stem of a wine glass and you're seeing things stretched out along its periphery. And so when we looked at the Sparkler galaxy, with Hubble, it just looked like a regular edge-on galaxy. And with JWST, you could resolve all of these tiny point objects. And this galaxy is at a redshift of 1.4, which is when the universe was about 4.5 billion years old. And we saw this and we were like, holy shit, this is incredible. And we were just like awestruck when we saw the image. And we were like, okay, wait, what are the properties of these star clusters? And so we went in and we age dated them. And when we age dated them, we found out that these are all not actively forming stars. These are like quiescent old objects. They are clusters of stars that formed when the universe was much younger that are inactive now. And these are very similar to something we see around our own Milky Way called globular clusters, which are really interesting for tracing the assembly of galaxies. This is the first time we have seen these in a galaxy so far away instead of in our local neighborhood. And so we were like, okay, can we do better? Can we now go look at a system that's actively forming stars that's farther away? So we did this search in a program called Canax, where we went and looked at a lot of galaxy clusters to see, are there other objects that are getting magnified by this gravitational lensing effect? Are they getting blown up in a way where we can see them in a lot more detail? So zooming in on just this small patch, and with a slightly better color scheme. So this is just that patch in the bottom of the MAX 1423 cluster. And in here, we found another object that is at a redshift of 8.3. So this is when the universe was only 600 million years old. So this is when the universe was 5% of its current age. And this turns out to be a system of 3 galaxies all at this epoch. And when we studied it, we found out that this is also lensed by gravitational lensing. It's like stretched out and sheared, in fact, a lot more dramatically than the sparkler. And when we look at this, this is when we try to reconstruct how it looks like in the source plane. So the folks at NASA sort of took our results and they helped us make this really nice artist concept of what the galaxy might have looked like. And we looked at the light coming from this overall thing, and it became really interesting when we realized that back when the universe was only 600 million years old, the mass of this galaxy is very close to what the mass of the Milky Way might have been at that epoch. So this is us being able to study the sorts of conditions that early stars in the Milky Way might have experienced when they formed. And this got a lot of press attention. It was a very interesting experience because a bunch of people sort of reached out to us to interpret what this might mean. And it also got shown in the Link NYC towers walking around New York, which was very cool. So I'm going to pivot topics a bit here, but the thing I want to highlight is when we do analysis for things like the Firefly and the Sparkler, we end up drawing from scientific topics across a whole bunch of different fields. So there was Bayesian inference to constrain properties, spectral modeling to model the light, and so on. And it becomes really difficult to sort of keep track of all of these different topics, even when you're working in large teams. So this brings me to the other side of my research, which is thinking about, is there a better way to search and find relevant literature when you're doing when you're doing a project? So we're going to switch from the distant universe to the abstract land of astronomy papers, right? Finding papers is difficult, right? Regardless of whether you're a new grad student or a new undergrad or a casual reader or a seasoned researcher. And a lot of times the way we find papers is either to go to a library, less common these days, or do a Google search or ask a friend or just go by word of mouth at a conference. And so a new thing that has come up in the last, I'd say 10, 15 years is the notion of doing something called a semantic search, which is searching by similarity in meaning. And this is giving a talk in 2021, talking about ways that I was trying to build to try to do these searches. And I say this is very much an emerging field back then, and not knowing how much this is going to blow up. And so the way this works is you take a paper or a set of papers, and you do some transformation on the material in that paper to convert it into a set of numbers. So this could be as simple as indexing keywords. So if JWST is mentioned in the title, mark 1, or by doing something more complicated, like searching for a certain phrase or a certain meaning. And then when you have many such papers, you can convert this into a space where those sets of numbers are now ordered by similarity. So two papers that have similar sets of numbers might have similar topics that they care about, and therefore are close to each other on the space, and two papers that are far away might have very different topics. And so you construct these kinds of spaces where like each dot is an academic paper with some data it's looking at, some analysis is doing, some results it has. And then when you ask a question, what it does is you take that question also and convert it into a set of numbers and project it into the space so that you can find nearby points and you can use that to answer your question. And you can find papers that are similar or relevant to the question that you're asking. So this worked well enough. And I used this for a while. I didn't think of making it public or anything. But then I was at a conference in Santa Barbara and I met a collaborator, Joe Chuka, who was like, do you know about these like really large models that are coming up? Like, have you tried doing this with GPT or something it's called? And I was like, I don't, but I can try it. And so we paired up and we formed this organization called Universe TBD, where we were like, we don't know, we'll see if these things work or not. And we tried to do a systematic reformulation of this problem. So the team's grown by a lot in the last few years. It now has close to 100 people, I think, or 80 something. And we participate in things like this workshop at Johns Hopkins, where we worked with people in psychology and social science and computer science and astronomy all together to conduct these sort of user studies. So this was the team at Hopkins. And we essentially went to 40 astronomers and we gave them a prototype of this tool. And we said, use it for 3-4 weeks and tell us what you like, what you don't like, what you would like this kind of tool to be able to do for you. So we were like, we don't want to create something in a vacuum. We want to make something that is practically helpful to astronomers working on current relevant problems. And so we got a lot of information from this. We got a lot of comments that are helpful to us, but also to LLMs at large. Things like we want specific answers. We want graceful refusal. If you don't know something, say you don't know something instead of making up an answer and say why you don't know it, right? And so that's the sort of thing that we were trying to architect into our model. And so we ended up making this thing called Pathfinder that essentially takes this corpus of about 400,000 astronomy papers. So this is a subset of all the papers that exist, but we make cuts for whether it's peer reviewed and whether it's current and all of these things. And we essentially made this pipeline that does two things. One, given a user question, it tries to answer to the best of its ability, and it tries to find a bunch of published academic research that it uses to compose that answer. So it cannot make anything up. because it has to be grounded in these papers that it finds. So here's an example. So between JWST and this other telescope called ALMA, we discovered a very high redshift rotating galaxy. And so if you were to just see a press release or a news article about this galaxy, you're like, oh, wow, that's cool. I want to find out more about it. If you saw the actual press release, you could go to the paper that this is based off, and you would know that this galaxy is called Rebels 25 and find out about it. But if you didn't know that, if you just saw the news article and you were like, oh, I want to go search for this in the way astronomers generally search, which is using the system called ADS, then that paper doesn't turn up because you don't know exactly what to search for, which would be Rebels 25. So this is where methods like Pathfinder come in, where you just type in what's the highest redshift galaxy with a cold disk, because that's what was in the article. And in its results, it tells you it's called Rebel 25, and it gives you the paper that is associated with it. So since I released it about a year and a half ago, it's now had close to 130,000 users, which is a significant fraction of the astronomy community, at least, that seems to be adopting it, which I'm very happy about. Other, bigger LLMs are also now starting to adopt these kinds of things, where they now have access to the internet and they can do information retrieval and grounding, which is good. So this is from Claude. Claude can also now tell you that Rebels 25 is the galaxy you're thinking of. But the thing Claude doesn't do that we really focused on is, again, the space in which all the papers live. So in addition to giving you this result, it also says that this is the part of the astronomy literature landscape that this galaxy and papers about galaxies similar to this are living in. And so you can sort of go in there and you can see sort of like that's the rough area, that's the kinds of studies that look at galaxies like this. And then you can even go into this actual landscape and click around and see what other papers look like. So you can do a bunch of things with Pathfinder right now, but the thing I really want to focus on is when we were developing this, we were guided by three main philosophies. One was that we want a tool like this to enable you to explore the landscape instead of just being given like, here's the right answer, this is all you need to read. We wanted to lower barriers to access. When I was developing, like the first place this was released at was at the International Astronomical Union meeting in South Africa, and a lot of people there wanted tools where they can search for things in local languages, but get results that are grounded in actual papers that are written in English. And the third is we wanted it to be interpretable. We don't want it to be a black box where you don't know what it's doing, how it's coming up with these papers. We wanted to make everything transparent and public. And so here's an example. Like this is asking what is a quiescent galaxy? And if you ask it in a different language, then it also gives you an answer in a different language. And this is because a lot of these models that Pathfinder and other tools are built on are natively multilingual, so this is great. But this answer is still grounded in the papers that it pulled from that part of the astronomy literature landscape. So you know that the underlying papers are still real. And then these are some other technical tasks where you can ask it to like give you a simplified answer and ask it about things like systematics or modeling that might not be very obvious from like a Google search or a ChatGPT search. So you can take this kind of landscape and explore it further as well. So you can, I just took this, there's a bunch of points here that you don't see, but it's all like clusters of papers. And you can make a chart that shows essentially the density of papers at different locations. So you can see areas where there are many papers because it's an old established topic and there's a bunch of research that's been done on it. And there are areas that are more sparse and there's not many papers because those tend to be emerging areas of research. And so we took this and we made a really pretty graphic that sort of shows this visually. And you can sort of see that similar papers are arranged by topic almost. So all the way up top, you have comets and the solar system, going down to exoplanets, going down to planet formation that segues into star formation, to the Milky Way, to galaxies, to galaxy clusters, to cosmology. So it's learned this really nice structure to organize the papers by, even though we didn't explicitly require it to do so. And there's this tool here that you can scan the QR code for. This allows you to like go look at the space, click on individual papers, explore it. You can zoom in and zoom out. It might not work the best on a phone. So you can always take a photo of this and then go home and try it. And it might look better on a laptop or a desktop. Okay, so I can show this later as well. So, all right, tell me when I can move on. Okay. So you can use this kind of space to do a lot of useful things now that you have it. You can take concepts that the Unified Astronomy Thesaurus or the UAT uses to classify different bodies of astronomy research and see what parts sort of intersect or overlap. You can take different telescopes that are observing and doing different kinds of science and see where papers made using that telescope live. You can also see whether these telescopes and missions are having impact in places where you didn't expect them to. So sometimes you would use a facility in a way that wasn't intended when that was constructed, and you'll see papers corresponding to that pop up in a different part. And most interesting to me, you can use this to see where current authoritative review articles on different topics are written. So here, the red points are basically up-to-date reviews on different topics. So you can see which areas actually need a new review to be written. Otherwise, people have to go scrambling around to get up to speed a lot more. And so this is sort of like an in-depth view of the central part of the landscape. And the way you read it is that mountains are the well-studied or well-established areas of research. The plains or plateaus are regions of active study where there's like a good number of papers, but not as much as the mountains. The shallow waters are emerging areas. So these are areas that have either come up in the last few years or are in the process of emerging. So there used to be a much deeper trench here between black holes and galaxies before JWST launched, for example, that is now getting filled up by papers that have been written in the last 3 years. There used to be a bunch of these mountains used to be a bunch of foothills back here in 2012 to 2014 before the ALMA observatory came online and sort of produced a massive body of work that has unified all of them. So studying this over time is also very interesting. And in the app that I just showed, you'll be able to filter by dates and see sort of when papers crop up. The last thing I'm going to quickly mention is you can use this to quantify trends in research. You can take this and you can break it down into a bunch of small clusters. And you can look at how old the papers in any given cluster are. And so you find that some of these are older clusters, some of these are newer clusters. And you can then rank everything by age and use that to see what topics are falling out of fashion, either because that question has been decided or we don't need observations of that anymore, and what topics are very much emerging areas that people are actively studying right now. So you can do a lot of prioritizing in terms of designing future missions and so on based on this kind of information. But this sort of is highlighting the potential of what you can do with models like this. I just want to quickly zoom out a bit and talk about generative models at large and just give you the perspective of someone who works with these a fair amount. So things like ChatGPT are a mixture of a lot of optimism and a lot of pessimism. Right, so on the right, on the left, I'm showing you a few really big discoveries in things like in vaccines or in protein folding that have been enabled by these kinds of models, fine-tuned to specific scientific tasks. And then on the right is a set of cautionary tales that you hear when these models are used, both in terms of students or people at large. And so while these techniques are extremely promising, there are also a bunch of potential pitfalls that you have to be very aware of when you use any of these models. So this is one of the things where there's this thing called the AI incident database. I highly recommend going and looking at this if you want to just see all the ways in which these can go wrong. It's a wonderful rabbit hole. But this was one where ChatGPT came up with imaginary references when asked a question. And this is sort of the reason we looked into developing tools like Pathfinder in the first place, where you could be grounded by actual literature when you're answering a question instead of just relying on the model. So there's should be aware of in terms of labor disruption, environmental costs, and more. So when we are as researchers developing tools that work with AI in different ways, I think I want to come back to the earlier thing I said about Pathfinder, but now generalize it across the board and say that we should really focus on making tools that help you sort of automate the things that are boring and not the things that give you genuine joy while doing research or while living your life. They should increase your quality of life. We have to make sure that these things do not stratify privilege, that they actually lower barriers to access, whether that's thinking of who bears the cost of training and operating these models, and in terms of what kind of service they provide. And finally, we have to really, really think about making these models interpretable, both in terms of the developers knowing the ins and outs of the models, but also end users understanding what the model is doing before it gives you an answer. And these should ideally be baked into the development process, not seen as something to be done as an extra. So, in terms of what I do, I think there's a bunch of routine tasks that I regularly do that otherwise cut into a significant amount of my research time that I've been able to use some of these models to automate or speed up. And so in that sense, it's been extremely useful. And in the interpretability part of this, there's interpretability being pursued across a whole range of scales. From what kind of inputs work best, this is something that I think any of us who use these models might have tried. And there's all the things all the way at the end, which is like what kind of biases get baked in when these models get trained, which are much harder to answer. But there is increasing work on this, but we can always ask for more. And so the reason I think I want to present this perspective is because I see astronomy as a sandbox that we can develop these tools in, that we can play around and test these things in without there being any risk to life and limb. In the sense that like astronomy produces these huge open data sets on the order of many petabytes especially from upcoming observatories like Roman and Rubin and Euclid. It has a set of well-defined ground truths in the sense the universe runs on. There are a lot of things that we can use because astronomical data sets are very challenging to analyze and to deal with noise and all sorts of systematics. But it is not life or death. There's no medical data, there's no financial data, there's no privacy issues here. And astronomers as a community that I have interacted with tend to be huge skeptics of black box models. So they're like, if I don't know how it understands, I don't buy it. And so when you develop these models in collaboration with astronomers, that interpretability part sort of gets baked in. So as citizens, like zooming out, what can we do? I think it's really important as these things become or integrate themselves more and more into our lives in ways both conscious and unconscious, to be informed of what their capabilities are, what their limitations are, and to know sort of what kind of biases they might carry. As a public, we can demand transparency wherever we have a voice, wherever we have a platform to speak about it. And we can push for further regulation in terms of making sure that they are aligned in the sense that the thing that they are asked to optimize while training is aligned with the sorts of things that humans would want them to do. And when we build tools, try to make them as safe as possible, as interpretable and explainable as possible right from the start, instead of trying to tack that on afterwards. And finally, just to bring up Chekhov's gun, like, if we make a gun, there's a good chance it'll be used. So just because we can automate something or we can make a pipeline doesn't mean we should. Technology is meant to make our lives better, but it is ultimately humans who decide how it gets used, and we should use our voice to speak up about this. There's this really cool report called AI 2027, which makes like near to middle term predictions for how AI might go in the future in terms of computational resources, social costs, and stuff. So if you're interested, please look that up. So with that, I'll conclude. Just saying that JWST, is this incredible observatory that's pushing the frontiers of what we're able to do. but the volume of literature that accompanies JWST observations and their analysis makes it really difficult to stay on top of it, especially when everything is becoming more and more interdisciplinary. And so things like large language models and like these vision language models can help as long as we make tools that are grounded by techniques that mitigate how much risk there is involved, and so that they're explainable and we can verify that the answers are actually accurate. And astronomy as a school of thought and as a source of data provides a great testing ground to try a lot of these techniques. So thank you so much for listening, and I'll take questions. Wait, sorry, I can't hear. Oh, sorry.
All right, and one thing Karthik didn't mention is a lot of the graphics that he showed, he drew himself. So really thinking about like, what can humans do better than AI? All right, so Q&A time. You're welcome to ask your question out loud, or if you want to write it, you can scan this QR code or go to the link and your questions will pop up on stage. Okay, let's start. Yeah, so what is a quiet or quiescent galaxy?
So quiescent galaxies are fascinating class of galaxies that don't seem to be actively forming stars. So if you think about galaxies as sort of people, star-forming galaxies are galaxies that are sort of like young from age, they're growing, they're doing a job, they're earning money. Quiescent galaxies are the ones that are retired and not forming stars anymore. There's many different ways a galaxy could be quiescent, but usually the way it works is the galaxy is formed stars by turning gas into stars over time. And no gas left, then you end up with a galaxy.
Yep. Yeah, so for Pathfinder, your AI model, if you had a totally different data set, so not astronomy papers or two different data sets, how would the model change?
So fascinating question. There's actually some domain adjacent things, so different topics in physics and astronomy, for example. So if you take nuclear physics, I have friends who work in that, and they wanted to see how the map looks. So the nuclear physics thing sort of sits almost entirely to the side of this, where the point it touches is neutron stars. That's the bridge. And so you see that, when you get to the neutron stars part, you can walk from the astronomy part to the nuclear physics part and back. But otherwise, it's a pretty distinct landscape. And each landscape tends to be structured differently according to how people in that field do research. The other part is I have friends who do cancer research, so we have been looking into a gene sequencing version of this, and that is entirely distinct. It doesn't touch this landscape at any point. And there it tends to have a lot more clusters because people tend to work in these big consortiums and do research as like giant groups of like 200-300 people. So astronomy tends to be very wide in terms of like, there's some papers that are single author where it's like, oh, you go work on like a very niche topic and write a paper on it. But in medicine, at least to the extent of my knowledge, it seems to be a lot more, you work as part of a big group, and so the topics. Yeah.
I'm gonna actually, just to make sure that everybody gets, we'll come back. Yeah. All right. Yep. In the pink jacket.
Yes. So
So even though she wouldn't, could she ask AI to do her Spanish homework for her?
So this is actually a class of AI use cases. When we did the user study, when we gave this tool to different astronomers to try to use it, some of them actually tried to make it do things like this, where they're like, instead of finding a paper for me, can I just ask it to give me a recipe for baking a cake or doing a homework problem? And the way we have tried to build it right now is that it will only answer if that answer is an astronomy question. And so if you're trying to do Spanish homework in astronomy, this will work for you. But like in general, these tools actually can do translation really well.
Question here.
Yeah.
How do we find out?
Ah,
How do we find the age of a galaxy?
you asked a question very dear to my heart. So when you look at, let's see if I can find a picture. Going back, way back. Okay. Yeah, when we look at a galaxy like this, right? It's made up of all of these different clusters that are of different colors, right? And it's the color of a galaxy that contains information about its age. So each of these clusters is made up of many, many stars, and different stars tend to have different colors based on their temperature. So hotter stars tend to be bluer, cooler, redder stars tend to be, or like cooler stars tend to be redder, and the hotter stars live for a very short amount of time because they're burning through their fuel very fast. The cooler stars tend to live for a much longer amount of time because they're going slowly through their fuel. And so when we see the color of something, we are able to guess how many hot stars there are, how many cool stars there are. And because we know the age of each of these kinds of stars, we can tell what the age of that cluster is. And then we do that across the galaxy and we can say how old the galaxy is. Yeah.
I'm going to do one from online. How do we see a galaxy or a galaxy with a black hole when it doesn't allow light to escape?
Excellent. Okay. So do I show spectra here? Okay, yeah, this might do. Doesn't have emission lines though. It's fine. We'll try to manage. So
There's
this,
also chalk.
oh yeah, perfect. Chalk would be great. Can people see when I draw on the board here, maybe? Okay. So this is wavelength on the x-axis, right? So wavelength goes from ultraviolet, like the highest energy on this side to the lowest energy on that side. So going from blue light to red light or ultraviolet to infrared and so on. And here I'm just going to call this brightness. So you can make plots that show how bright a galaxy is at different wavelengths, right? And so this basically ends up giving you something called the spectrum of a galaxy, and it changes depending on the galaxy, but it might look something like this. And different parts of the spectrum contain different amounts of information about what this galaxy is made of. So when you have these very sharp excursions, these are called nebular emission lines, and these generally come when high energy radiation passes through gas of some sort and excites the atoms in them. And these atoms emit light when they get de-excited. So when you see, so black holes tend to do a whole bunch of different things. Black holes that are really massive affect the galaxy that they grow in. And as matter falls into the black hole, it tends to form something called an accretion disk, where a lot of matter trying to fall into a black hole at high energy gets compacted and experiences tidal forces and essentially gets superheated and emits light. And this light ends up showing up in these emission lines. So without a black hole, a spectrum might look like this. And with a black hole, you essentially get a much broader emission line at certain frequencies. And that lets you realize that there is a black hole, that black hole has a certain amount of mass in it, and so on. Because this is the width of this line contains a measure of how much the gravitational field of the black hole is influencing the accretion disk. So this is one way of doing it. There's many other ways. Black holes also end up driving these giant jets that are visible at radio frequencies. Sometimes they also emit X-ray radiation that can be seen with X-ray telescopes like XMM Newton and Chandra. But yeah, I can talk about this more later. Basically, black holes emit light, or like black holes directly don't do anything, but they influence the galaxy around them in a way that emits light that you can see and measure.
Question. I see. Could you say that one more time for me, please?
Yeah.
So let's see. How old are most galaxies? Let's start there.
So galaxies can be of a whole wide range of ages. Some are extremely young, which would be a few hundred million years, and some are extremely old, almost as old as our universe itself, so a few billion years. Now, galaxies grow older at the same rate that everything in the universe grows older, which is they grow older by 1 second per second. But galaxies take different amounts of time to reach. Basically, light from galaxies takes different amounts of time to reach us. So the farther away a galaxy is, the longer that light will have to travel to reach our telescope. And that depends on basically how. So you see the galaxy when it was younger than it is today.
That leads to a question from online. If objects we see via telescopes or if the light of objects takes millions and billions of years to reach the telescope, how do we know if they still exist at this moment that we see the light?
Short answer, we don't. If the closest star to us explodes, we will not know for another 4 years until the light from that explosion reaches us.
Okay, we'll do a couple more questions.
Yeah.
Yeah, so how do you know that a large learning language model, specifically Pathfinder, is not hallucinating?
So I can tell you the general answer and the specific answer. In a general case, we don't really know. What people do is create benchmarks of things where you know the correct answer and run these models through all of the questions and see whether it's making up any of the answers. And you can give it essentially a truthfulness score based on how well it does at that benchmark. So that's one thing. In Pathfinder, the thing we specifically did was try to ground it by having it search for papers first, and then limiting what it can spit out as an answer to be conditioned on only information in those papers. So if the information that you're looking for doesn't lie in those papers, then it is forced to say, I don't know, because that information wasn't available. So that's how we mitigated it in this case.
Okay, do one and then to our final.
Yes. Mm-hmm. Right. Okay. So
you're talking about galaxies that formed when the universe was like 500 million years old. And you said that's 5% of the universe's life. So how
Right.
much is that in like human analogy?
So I'm going to show a few different examples here that might help. So the galaxy right here, this central galaxy is a massive cluster galaxy at low redshift. So that central galaxy is going to be something like 70, 80-year-old as a human. So it's very old, not forming stars anymore, not doing anything, just sitting around with all of its family around it and chilling. It's had a good life. The Firefly, no, let's go back to the Sparkler. So the Sparkler, this galaxy is when the universe was 4.5 billion years old. This galaxy is actively forming stars. It's growing. It's thinking that it will make a name for itself. It's about 35 years old. It's very much at the prime of its life. This galaxy, the Firefly Sparkle, is extremely, extremely young galaxy. This is barely 2.5 years old. So it has its whole future ahead of it.
Awesome. Thanks for help with the clarification.
Yeah.
Okay, and our final question, but you can come down after we're done to ask Karthik more questions. Yep.
Mhm. Yes, no, yeah, it's meant for everyone. So I've had a lot of high school students use it, or people who are very much not in astronomy but want to know the answer and might feel like they can't believe what Google tells them. So you can ask it anything. I have asked it to compose poems about different astronomical topics. It made me a rap about the Hubble tension at one point, which was very, very well done, to the point where I was like, okay, I could actually use this in a class, or engaging with friends and so on. So yeah, if I would highly encourage, go explore it. Like, tell me if also, like, just send me an email if something looks interesting, and I can look further into it. Yeah.
Usually to assign people seats as they take horrible exams in this classroom, but today we are changing the energy and we'll do it for fun. So if I call your number, please shout out. You can get your stuff on the way out, so you don't have to come down now. For prizes today, we have 3 mugs and 1 tote bag, and they all have a bare Rubin quarter in them and a magnet. All right, so please scream loudly or something so that I don't skip over you. Last time I overdid it, so I owed 1 person, my poor student. It was an IOU that I gave her. Okay, J7, D14, M17, E2, I17. Got it? Okay, we got 1. G8, B. All right, we got 2. Woo! B5.
We have 3.
Okay, I think that's all 4. Raise your hand if I called. All right, congrats to our winners. Woo! Okay, now I'm going to go over some logistics for observing. We are going to observe. There are 2 options. You can choose both. One is to observe on the roof of this building. It is a historic dome, so it is unfortunately inaccessible. You need to go up 2 flights of stairs in this building and then 1 fairly steep set of stairs to get into the dome. It is a historic dome, so it is dark, it is cramped, there is no nice furnishings. So when you go in, there's only going to be about 15 people who can fit inside at once. So you can line up, you can admire the view from the roof, you can wait in the staircase where it's going to be much warmer, but there will be some waiting involved. So there's no rush to go straight up to the roof because you'll be in line anyway. We also have a telescope set up on campus that requires no stairs to get to. Today, it is in front of the building in the center of campus called Low Library. There's a statue in front of it. It's between the Low Library building and the statue called Alma Mater. If you put into Google Maps Low Library, you'll be able to find it. You are welcome to go to both. But again, the roof is unfortunately not accessible.